In this video, we're going to have a look at the types of stationary points. So what I mean by types of stationary points is we're looking at ways in which we can classify each stationary point. Now, if we think back to our last video, we classified a stationary point as a point on a graph where the gradient itself, or the slope, goes to 0, in which it would produce if we drew the tangent, we would get a horizontal tangent. So the stationary point a stationary point is a point where the gradient of a graph is 0. Alright, so over on the right here, what I've got is a graph or a polynomial of a various order. If we look at the graph itself and then we locate the stationary points, what we see is we've got a stationary point here, one here, one here, one here, and one here. So observe the different shape that the stationary points have. So in this first one, what we see is the gradient of the graph. It's positive because it's growing, but then it switches over to negative. So this particular type of stationary point, we call it a turning point. In this case, the turning point goes from being positive to negative. Conversely, if we have a look over to the second stationary point, it's still a turning point. However, this particular turning point, it's gone from being negative to going to positive. And similar with the fourth one, it goes from positive to negative, and then the final one, it's negative to positive. But more interestingly, if we look at the second turning point, it's a little bit different from all the other ones. Rather than being, say, positive to negative or negative to positive, this particular turning point, it goes from being negative back to being negative. So this particular point here, it's not a turning point, it's still a stationary point, but it's called a point of inflection. So what we mean by that is a point of inflection is such that the gradient itself of the graph doesn't actually change, but rather it just stands still for a moment and then it goes back to what it was originally. So classifying these types of turning points, as I mentioned, we've got types of stationary points. What we're going to find is that we have 4 types. Alright, so the 4 types of stationary points we can have are, the first ones we'll go for is, we'll have the turning points. So the turning point itself, if we look at the first one, we go from being positive to negative, negative to positive, and then we go, well, that's a terrible one. Let's go negative to positive to positive, and then finally negative to negative. So writing that out, we're going to get positive to negative, negative to positive, and then positive to positive, and then finally negative to negative. So one thing to keep in mind is that we've got these 4 types of turning points and also, 4 types of stationary points. On the ones on the left here, so positive to negative, negative to positive, these are turning points. And these ones over here, they're called points of inflection. One thing to keep in mind is that regarding points of inflection, you will see another type of point of inflection. So these ones, they're horizontal points of inflection. What you'll be able to see in the future is something called a a vertical point of inflection, in which case it has quite significant consequences on the math that you're doing with that one. But for now, we'll just leave it as being able to see points of horizontal inflection in that we see it go across like that. Alright, so this concludes the concept of the types of stationary points. Let's look at how we can analyze, so how we can classify, say, a function based on its stationary points. So consider in this question here, we've got find and classify the stationary points of the following function, and the function is defined as y equals x cubed minus 3x squared minus 9x plus 5. So the question, it says find the stationary points, and then it says to classify the stationary points. So what we're going to do here is, firstly, we need to find where the stationary points are, and then we need to classify the stationary points in terms of, are they positive to negative, negative to positive, and so on. To do the second part, we'll use a Sine diagram. But to begin with, firstly, what we're going to do is find the stationary points. So if we recall back to the video, or the previous video, the way in which we do it is we have a three-step process. First one is we take the derivative of our function, then we set the left-hand side to 0, and find the values of x using the null factor law. And then when we find the values at x, we resub them back into the original equation to find the values of y, and that will give us the x and y locations. After we do that, we'll classify how the turning points are changing. So jumping into the first bit, we'll go 1. To find the derivative of this function, it's going to be dy over dx. We'll use a simple power rule because it's quick. 3x squared minus 6x minus 9. Then part 2, we'll set it to 0. So let dy over dx equal 0, in which case we're going to find the roots of the function, which in turn tell us the stationary points. So 3x squared minus 6x. Right, we've got one equation and one unknown. Solving for x, firstly we'll divide through by 3 to get rid of that non-monic component. Alright, and now we'll solve for x. In this case, it's going to be x squared minus 3x minus x minus 3. So positive x minus 3. And then factorizing, we know that the factors for this particular problem is x minus 3, x plus 1. Alright, so in which case x equals positive 3, or it equals negative 1. Awesome. Now to find the points, we simply go when x equals negative 1, y equals negative 1 cubed minus 3 negative 1 squared minus 9 times negative 1 plus 5. This will come out to negative 1 minus 3 minus negative 9, so plus 9 plus 5, negative 4 plus 14, and that's simply positive 10. So the first location is at x equals negative 1 and y equals 10. And then we're going to go when x equals 3, y equals, it's going to be 3 squared minus 3 squared minus 9 times 3 plus 5. The 3 squared minus 3 times 9 minus 9 times 3 plus 5. The 3 squared is going to, sorry, this will be 9 minus 20, oh, that should be cubed actually. Let's take it a step back. 3 cubed, that's 27. 27 take 27 plus 5. This will cancel with that. Then the answer will be negative 22. So stationary points are at negative 110 and 3, negative 22. Done. Okay, so that's the first part of the question. That's the finding the stationary points. Now we need to classify the stationary points. So we want to know what's going on at negative 1 and 10 and what's going on at 3 and negative 22. So the way in which we do this is we're going to grab the function 3x squared minus 6x minus 9, so the derivative. Then we're going to draw a sine diagram based on this function here. So we'll go for dy over dx, and we know it's 3x squared minus, what was it, 6x minus 9. Let's draw our sine diagram. So go something like that. This really should be drawn with a ruler, but this program doesn't have one, so we'll have to make do. We'll say that we'll go negative 1 is here, therefore 0 will be here, and then 2, 4, 6, we'll say positive 3 is over here. So perfect. Alright, what we're going to say is that our stationary points are here and our stationary points are here. Now what we want to know is, in between these stationary points, what is the behavior of this function? So the way in which we can do this is we can do a bit of synthesis. So what this would involve is we'll pick some values. So we'll pick, say for example, we'll go negative 2, pick positive 4, and we'll pick 0. So these guys here. What we're going to do is we're going to sub in these numbers here to determine the location of to determine whether the value of y is above or below the x-axis when we substitute in these values, in which case it will tell us whether we're going to see something of the likes of, say, negative, positive, negative, or positive, negative, positive, something like that. Alright, so starting from the negative 2, we'll go when x equals negative 2. So in this case it will be dy over dx, and we can use our Leibniz notation like this, negative 2. Substituting that in will be 3, negative 2, all squared minus 6 times negative 2 minus 9. This is going to come out as 3 times positive 4 minus 12 plus minus 9. 12 plus 12 minus 9, 24, take 9, and this will come out to be, I believe, 15. So in which case dy over dx is greater than 0. So therefore in this region here it's positive. Alright, now for the next one, we'll go dy over dx, and we'll say when x equals 0, what we're going to get is 3 times 0 squared minus 6 times 0 minus 9, and therefore that's going to come out to be 9, or minus 9, and therefore because it is dy over dx is less than 9, it's less than 0, so therefore it's negative here. And then finally we can probably already tell looking at the original function that what it's going to be, but when we set it to 4, we're going to say 3 times 4 squared minus 6 times 4 minus 9. This will be 3 times 16, 6 times 4, so that'll be 24. So pretty much, I believe that's 48 minus 24 minus 9. It's going to be greater than 0. So dy over dx is greater than 0. So our Sine diagram is going to go positive, negative, positive. So what we find is that the nature or the classification of the turning points, in the first instance, we're seeing positive gradient going to negative gradient. So it's going positive to negative. And then the second one, it's negative to positive. So it's going to look like that. Happy, smiley face, negative to positive, like so. So what we've done is we've classified the stationary points using our Sine diagram here. So this would be how we attempt this sort of question. Again, there's quite a lot going on here, but remember the emphasis on these sort of questions is the ability to explain what the stationary or how the stationary points are. So in this sort of question, say for parts 1, you can use simple power rule. Parts 2, to solve this sort of question, if you wanted to, you could use the solve_n function on your calculators, which would alleviate a lot of the calculations here. And then for 3, you could easily use the graphing feature or the graphing feature on your calculators, and then use your xcal and ycal values to get these points here and here. So looks like there's a lot of working out, but remember, you've got technology to assist you in all of these calculations. The important thing to remember is the process. So we'll leave it here for now, and in the next video we'll look at something that requires a little bit more process. So the next step on